Welcome back, everybody. My new course, Actor-Critic Methods from Paper to Code, has finally dropped, and in this video I'm going to give you a free preview of how to code the twin-delayed deep deterministic policy gradient algorithm in Pytorch. Let's get started. But really quick, few announcements before we put code to editor. So this content is supported by my Udemy courses. I also have a course on deep Q learning, and in both of my reinforcement learning courses I show you how to go from reading a paper to implementing a paper in Pytorch code all the way from start to finish. I explain every line of the code as well as go through the papers paragraph by paragraph, explaining how to interpret the paper, how to understand what they're saying, and how, most importantly, to put that in the context of writing functional code. If that sort of skill is appealing to you, check the links in the description. I'll be running sales intermittently on all my courses, so go ahead and get the best price possible by clicking the link down below. Now, all of that out of the way, let's go ahead and get started with our imports. Of course, we need NumPy, Torch, Torch Optim, and we'll need OS for model checkpointing. Now, twin delayed deep deterministic policy gradients is a solution to function error approximation in Actor-Critic methods. Again, I go through all of this in detail in the paper, but the basic idea is that we have overestimation bias and we also have variance and bias due to accumulation of errors due to the fact that we're using a deep neural network to approximate the agent's policy and value function. Now, we have to make a number of modifications to the deep deterministic policy gradients algorithm. We have to delay the policy updates by every other step. We have to smooth the calculation of the target in our critic update. We also have to perform a double Q learning type modification to our learning rule for the critic as well. That's the algorithm in a nutshell, and the cool thing is that you can bolt these modifications onto other algorithms like PPO, Solved Actor-Critic, etc., etc. All that said, let's talk about what we're going to be doing today. We have to code up a number of helper classes for our deep deterministic policy gradient algorithm agent. What we're going to need is a replay buffer, a critic network, an actor network, and an agent class, and then we'll have a separate file for the main loop. So let's start with the replay buffer. And the basic idea is that we want to create a buffer of memories that we sample uniformly. So our constructor is going to take a max size, an input shape, and number of actions. Here, number of actions is a bit kind of a misnomer. This algorithm deals in particular with continuous action spaces. So we aren't really dealing with a number of actions, we're dealing with the number of components of an action. So let's go ahead and start saving our member variables. Our memory size is going to be the maximum size for our memory because it shouldn't be unbounded. The memory counter keeps track of the position of our first unsaved memory so that we can insert a new memory there. And now we get to the actual memories. So we will save the state memory, the new state memory, action, reward, and terminal memory. Okay, so one important point here is that the terminal memory is going to be a memory of the done flags from our environment. The reason we need that is because the value for the terminal state, the value function for the terminal state is identically 0, and the easiest way to take that into account is with an array of masks that we will use to perform some masking of our critic values later on in the agent's learn function. Next, we need an interface function to store new memories in the buffer. And the first step in that is finding out what is the position of the first available memory. So we just take the modulus of the memory counter with the mem size. So when we completely fill up the buffer, we will go ahead and loop all the way back around to the beginning and start overriding our earliest memories. And then we just go ahead and insert the relevant data in the appropriate array. So dot reward memory. And most importantly, we want to increment our memory counter. Next, we need a function to sample that buffer. And the first thing we want to know is we have filled up an array of all zeros, and we don't want to sample those zeros because training the agent on zeros doesn't make any sense, right? What we want to do is we want to train the agent on memories that have actual data from its experience. And we do that by finding out what is the minimum of either the memory counter or the mem size. So you don't want to take the mem size because in the event that the memory counter is less than it, because then you'd be sampling zeros. And you don't want to take the mem counter if mem counter is larger than mem size, because then you're going to be going past the end of the array. Then just go ahead and select an array of integers at random from 0 to maximum, and go ahead and perform the indexing on the arrays and return the relevant values. Okay, that is it for our replay buffer class. Now we can move on to the network classes for our agent. So we will deal with the Critic Network class first, and the Critic Network is what tells the agent the value of a particular state. This is part of the Actor-Critic paradigm, where you have two separate components of your agent, one that decides how to act and the other one that says, hey, that action sucked, choose something else. So our Critic Network, as per usual, will derive from the base nn.module class. This is typical with Pytorch classes that extend the functionality. Our constructor is going to take several parameters: a learning rate beta, input dimensions from the environment, fully connected dimensions for the first hidden layer, second hidden layer, number of components of our actions, a name, because we're going to have target networks as well as online networks. So we want to keep track of which network we're saving in our checkpoint file, and a checkpoint directory. And then we want to save our relevant parameters. And then we need a file to save our checkpoints. And the reason you want to do this is because the training of a model takes a fair amount of time, although TD3 is significantly faster in terms of efficiency than, say, deep deterministic policy gradients, but you're still going to want to do model saving. In particular, you're going to want to save your best model for evaluation later. And I just facilitate that with the creation of a checkpoint file, and I always use _algorithm name. So that way, if I'm making a YouTube video, for instance, and sticking stuff in one directory, I don't overwrite, my DDPG agent with a TD3 agent. That would be bad. So Next, we can define our actual neural network. And so we're going to take the concatenation of the input dimensions and actions, the components of our actions, right from the very beginning, and we're going to output FC1 dims. And then we will have an output layer. And that is single valued because the critic provides a scalar value, which is just the value of a particular state or batch of states if you pass in a batch. Next, we need our optimizer. And we need a device as well. And if you have a GPU, you absolutely want to use that. Otherwise, you can use the CPU. I'm going to use the continuous lunar lander environment for this because it's a relatively straightforward environment and something that you can solve on the CPU if you have to. If you have a GPU, you can substitute in the bipedal walker environment. That's what I do in the course because it learns within 1500 episodes most of the time. There is run-to-run variation where sometimes it goes off a cliff. That just happens in Actor-Critic methods. And reinforcement learning in general, it does suffer from reproducibility errors. But either way, either using the continuous lunar lander or on the CPU or the walker on the GPU is going to be just fine. And then you want to send your network to your device. Next, we want to define our feed forward for the network. I have one too many parentheses here. So we want to concatenate the states and actions at the input layer and pass them through the first fully connected layer. It's f.relu, sorry. We want to activate this. FC2, and then activate. And then finally, we pass it through our final layer. And return Q1. Next, we need two functions to save checkpoints and load checkpoints. And we're going to save our state dictionary to a checkpoint file. Say self.load state dictionary tload. And the load checkpoint is just the inverse operation, taking the data from the file and sticking it in the state dictionary for our network. Next, we need our actor network. And again, that derives from nn.module. A learning rate alpha, input dimensions, fully connected dimensions, number of actions, a name, and a checkpoint directory. And then we want to save our parameters. And now we can define our deep neural network. And the actor network is approximating the policy, so we're not passing in actions. In fact, we're using this network to determine what action to take. And so our output layer, I call mu. That is from the convention from deep deterministic policy gradients. You can call it pi if you want to, approximate. If you want to call it pi, you can call it whatever you want. I'm just using the nomenclature from the original DDPG paper. And this outputs the components of the action. This is a deterministic method, so we have to have some way of handling the explore-exploit dilemma, which we'll deal with later. But this is a totally deterministic function. You give in one set of inputs, you should get one set of outputs out. All right, now we can handle the feed forward function. We just pass the state forward through the network. Okay, so we do want to activate the output of our actor network in this case, and the reason is the tangent hyperbolic bounds it between plus or minus 1, and keep in mind that if you have an environment for which the actions are outside of that bound of plus or minus 1, you want to multiply that by the max action for that environment there. Next we have our saved checkpoint files. You know what, I'm just going to copy these up here because it is identical. So yank those and paste here. All right, so that is it for our networks. Next, we can handle our agent class. So the agent class ties everything together. And the reason I separate out the code this way is because an agent has an actor and critic network. An agent is not just the actor and critic network. It also has a replay memory, as well as some other hyperparameters from our environment, as well as the way they solve the problems of exploration, exploitation with respect to noise. So it has a bunch of other stuff, and so it doesn't make sense to have the networks themselves be the agent. So that's why I structure it that way, just to be object oriented and all that good stuff. So our initializer takes a whole gaggle of parameters. We need both learning rates, alpha and beta. We need the input dimensions, a parameter called tau. If you go back and see my video on deep deterministic policy gradients, tau shows you how to go from tau shows you how to do the soft update rule for your target networks. It's just a hyperparameter of the agent. We want to pass in the environment because we're going to need some max and min actions later. We need our gamma, which is of course the discount factor per update. An update actor interval, how often we're going to update our actor network. That's the delayed part. That's every other every other learning step. The authors of the paper use a warm-up period where they let the agent take totally random actions without noise for the take totally random actions for the first 1,000 steps, or 10,000 steps for some other environments. We'll use 1,000 in this case. Number of actions, that is the number of components of actions. Max size for our memory. 1,000,000 transitions. Layer 1 size. We don't want to shout. That's 400. That's from the paper. Layer 2 size of 300, also from the paper. A batch size of 100. That's what they use. Pretty cool. A noise of 0.1. So there are going to be a couple of noises in this problem. This is the noise for exploration. So then we go ahead and save our parameters. So since we're adding noise to the outputs of our fully deterministic policy network, actor network, we want to make sure they're constrained into the acceptable range by the environment. So we need to keep track of the max and min actions for our environment. Since we are delaying updates for our actor network, we need to keep track of how many times we've called our learn function, and we'll do that with the learn step counter. We also need to keep track of how many actions we have taken, how many time steps through the environment, in other words, so that we know when the warm-up period has expired. And we'll go ahead and save the update actor interval. Now we can go ahead and define our our networks. And we'll need a critic 1. And this is because the TD3 algorithm relies on 2 different critics for the update rule. It's part of the double Q-learning update rule for the Critic Network. And again, I go into great depth on why in the paper. Or sorry, in the course. It's very hard to talk and type simultaneously, at least if you're an untalented hack such as myself. 2. All right. And then we need our target networks. Now, the learning rates for these are just apocryphal, or vestigial, I guess, or they're not really needed. We're not going to be doing gradient descent on these networks. We're going to be copying parameters from the online networks to the target networks. So we have to pass in the learning rate just to be compliant with the constructor for the network, though. Okay, so those are our actor and critic networks, both the online and target. We have 2 other things to worry about. We need to keep track of our noise for the exploration portion of the explore-exploit dilemma, as well as we need to call the update network parameters function. And we do that so that we can set the initial weights of the target networks equal to the exact weights of the online networks. And I'm going to pass it in with a value of tau equals 1 so that we get a copy exactly instead of a soft update rule. Next, we have the agent's choose action function. And it takes the observation of the current state of the environment as input. The first thing we want to know is, are we still within our warm-up period? And if we are, then go ahead and get a random normal number with a scale or standard deviation of self.noise. I can already see that you guys can't see all of that. Let me clean that up for you. But if we're outside of the warm-up period, what you want to do is find the deterministic action. Float self-actor device, and then pass it through your network. It's actor dot device, not underscore. And then regardless of how you select a deterministic action, we're going to go ahead and add some noise to it. Equals mu plus tensor np random normal self dot noise. And again, this is debatable whether or not you want to go ahead and add noise to something that's already noisy. It doesn't matter. It's purely in the warm-up period. It's purely exploratory anyway. So in my mind, it's not critical, but this is how I did it. Then we do have the problem of we are adding noise to a deterministic function that is bounded at either end of plus or minus 1. And for certain environments, plus or minus 1 may very well be the full limit of the environment. And in which case you would select an action that is beyond the limit of that environment, right? If you add noise to something that's already at 1, you're going to get something larger than 1, assuming the noise is positive. And so we have to go ahead and clamp that to make sure it's within the boundaries that are acceptable to the environment. We want to clamp mu prime between min action, max action, 0. And then we want to increment our time step. And that's so that we actually get out of our warm-up period. And then we want to go ahead and return our action. And we have to do all of this convoluted dereferencing due to the way that Pytorch handles tensors. Not a huge deal. We simply have to pass a numpy array into the environment for an action. Next, we need an interface function to store transitions in the agent's memory. And that may look a little bit silly, and I can, see where you'd be coming from if you said that, but that is kind of the price of object-oriented programming, where you're left with interface functions between abstract data types, right? Whatever, it is what it is. That's the paradigm we live with. So whatever, we just move on. So next, we have to address the question of what if we haven't filled up our replay buffer with usable memories? So remember, our replay buffer is initialized with a bunch of zeros, and obviously doesn't do any good to learn from memories of zeros. And so the question is, do you let the agent play it enough time to fill up its replay memory before you start learning? Or do you just wait until it's filled up batch size and then start learning, which is what we opt for. So we say if mem counter is less than batch size, return. Next, we want to go ahead and sample our memory. And then we want to go ahead and convert those numpy arrays to tensors. And the reason I write the replay buffer class the way I do without reference to Pytorch tensors is so that you, the student, can go ahead and use this, or even me when I'm writing this stuff in different frameworks. That way the memory isn't framework dependent, right? It only depends on NumPy. It doesn't depend on Keras or TensorFlow or Pytorch. Okay, couple comments on that. You may notice that I'm being very pedantic about sending everything to Critic 1. Doesn't really matter. You could send it to the actor or really any of the devices because they're all the same device. It doesn't really matter. I just, for whatever reason, chose Critic 1. I don't know what I was thinking. It just, whatever. Second thing is I'm being very careful about the D types, and that is by design. And the reason is that Pytorch is quite particular about the data types of the tensors you pass to it. So you have to pass everything to the device so that way it's a CUDA tensor, and you have to make sure that it is either a like a double or a single or a long or whatever. You have to make sure it's the right data type. So I use t.float so that it's 32-bit instead of 64-bit. Otherwise, it kind of barks at you. So now we come to the really interesting part of the problem where we are going to do our updates. So what we want to do here is start calculating our update rule. So we start with the target actions. By passing the new states through the target actor network. Oops, excuse me, plus clamp t.tensor mp random normal And so this is straight from the paper. Basic idea is that we're performing smoothing of the actions we chose from the target actor network, and we are clamping in the range of plus or minus 0.5. And by smoothing, I mean adding in random noise. But that could also be outside of the bounds of the permissible actions of the environment, so we have to clamp it yet again. So those are our target actions. Now we can get the action value functions for those target actions. According to both critics, target critics. And then we do the same, similar for the online Critic Network. So we say Q1, and this is the action values for the states the agent encountered and the actions it actually took during the course of the episode, according to the first critic. And likewise for the second critic. But then we deal with the question of what happens when the new states, the state underscore, are terminal. The action value functions for terminal states are identically 0. So we have to make use of our done mask. So we say Q1 underscore done equals 0. Q2 underscore done equals 0. So everywhere done is true, every state, every new state in the batch, it will set the value of Q1 and Q2 to 0. Then we just do a little bit of dimensional manipulation. One underscore dot view. Good grief. And then we have the other innovation of the paper, the the double Q learning update rule. We want to take the minimum of either Q1 underscore or Q2 underscore as our critic value. Then we say target equals reward plus gamma times critic value underscore. And then we want to add in a batch dimension for dimensional requirements, I guess. Target dot view one. Now we're ready to actually perform our gradient descent step. And we want to go ahead and zero our optimizers. And then we can calculate our loss functions. U2. back propagate, and step our optimizers. And then increment our learn step counter. And then we have the question of, is it time to update our actor network? And if it's not, then go ahead and return. But if it is, then we are free to go ahead and update that network. And as I'm looking at this, I have a feeling I forgot a parenthesis somewhere. I guess we'll find out in a little bit, but I wouldn't be surprised if I did. Okay, so the first thing we want to do is update 0 our gradients on our actor. And then calculate our loss. And so we are passing the state through the Critic Network and getting the actions for those states as according to our actor. And then we want to take the negative mean. The actor Q1 loss, and then back propagate. Finally, we want to update the network parameters every other step. Now, there is a whole lot of logic that went into that. This is one of the most well-written, most thoughtfully argued papers I've ever read. It is quite dense, quite mathematical. It took me many readings to actually really understand the arguments they were presenting. I really love the paper, and this paper alone is worth the price of admission in the course because it is so well written, so well argued. It is truly a beautiful paper, and this is a truly state-of-the-art algorithm. I mean, the results it achieves are in a totally separate league compared to things like PPO, soft Actor-Critic. It's a whole different level of performance in the case of continuous control tasks. We aren't completely done yet. We have to deal with kind of an ugly function, the update network parameters, as well as a couple of functions to save models. So let's go ahead and get through that. And so this is basically identical to the DDPG case. So if you've worked through my video on that, this should be familiar to you. But if not, it's okay. We're going to go through it. Now we have to handle I've definitely forgotten a parenthesis somewhere. Let me scroll up and see where that is. Likely place for that to happen would be up here. Random normal. T.clamp. That seems okay. Right there. Yes, there we go. So I've forgotten my parenthesis there. Okay, so that explains that. All right, perfect. Sorry, now we can move on. I actually caught a typo before we got to running the program. That is a first on this channel. So we have to deal with a corner case, and the corner case is that from the very beginning, when we initialize the actor, we want to set the target and online actor networks equal to each other exactly. More specifically, we want to initialize the target networks with the values from the online networks. But every other time step every other time step, because it's every 2 time steps we do the network parameter update. But every time we update the parameters after that, we're using the soft update rule. So I'm going to say if tau is none, then tau equals self.tau. So that'll take care of that corner case. And then we are going to get all the parameters from all the networks, iterate over them, perform the update rule, and store those values in a temporary dictionary and upload those temporary dictionaries to the actual network. So let's do that. And this is somewhere that the code definitely has room for improvement. This is quite ugly. I don't like this function at all. It's just something I got working and then never really changed. And this is quite clunky, particularly in light of the fact that we have so many networks. And then we convert these to dictionaries. I'm debating on whether or not to keep my nomenclature from my first solution because it screws me up all the time. You know what? I'm going to get rid of it. Critic 1 equals dictionary 1 params because it cleans up the code significantly. 2 dict 2 params. Actor. Will that break? No, that should be fine. Target actor equals dictionary target actor params. Now we want to iterate over these dictionaries. So for name in critic 1, yes, critic 1 subname equals tau times critic 1 subname dot clone plus 1 minus tau times target critic 1 subname dot clone. And that needs to be put on a new line. I can already tell. There we go. And then I am going to copy this. Yes, and of course modify it. Name in critic 2 name target critic critic 2 target critic 2, and then we need to do something similar for the actor. Name in actor subname tau times actor name dot clone plus 1 minus tau times actor name clone. And this is the soft update rule where you kind of gradually move the parameters rather than do an abrupt online copy. And then we want to go ahead and upload the state dictionary. So self.target critic 1 load state dictionary critic 1. Is it critic 1? Yes. Target critic 2 and target actor. Let me double check this to make sure I didn't make a mistake. Okay, yeah, that is correct. All right, now we're in the home stretch. We just need 2 functions to save our models. And this is an interface function that we have to live with due to the nature of object-oriented programming. Target critic. All right, and that wraps up the agent class. Now we're ready to go ahead and code up our main loop to test it all out. I have an unindent error in line 111, and that's interesting. Let me take a look. Unindent does not match any. Let's try that. There we go. All right, that was a simple one space error. All right, so let's go ahead and start our main loop, our main file. So we will need Jim, NumPy, and we will need from TD3 torch port agent, and I will need, so I will have to do a copy. I'll have to import that file from elsewhere, but I believe that's all the imports we need. So you can get that plot learning curve from my GitHub. Just do a git clone. I will leave a link in the description. I need to get better about that. My apologies to you if you've ever looked for my code and couldn't find it easily. I always leave a link to my GitHub in the description at the very bottom, but it's not always clear where each particular file lives, and I fully acknowledge the inadequacy of my documentation. I need to fix that. It is on the list, but nonetheless, you can do a git clone to get that file from my GitHub. It's just a function to plot a learning curve. It's nothing special. First thing you want to do is make your environment lunar lander. I think it's v2. It'll probably complain. I might have to look up the documentation on that, but let's go ahead and make our agent. Learning rates of 0.001. Tau of 0.005. Batch size of 100. Layer 1 size 400. And actions equals env action space shape 0. We'll play 1,000 games, and we need a file name, and we will say we'll just do in one line here plus lunar lander continuous plus string and games. Let's add an underscore there, plus underscore .png. There we go. No, underscore games.png. That's what we'll do. And so that'll be our file name for saving our plot. The best score is going to be the minimum score for the environment, so that way we'll save a model right off the bat. Score history is an empty list. If you wanted to load a trained model, you would do it here. And I'm going to have to do some make directories on this before we play. So for I in range and games, we want to reset our environment. The done flag and the score for each episode. First thing you want to do is select an action. And get take the action and get the new state reward done flag back from the environment. And go ahead and store that transition. Perform a learning iteration. Keep track of your reward and set the current state to the new state. Append your score and calculate your average. And then we'll say if your average score is better than the best one, set the best score to your current average and save your models. And then print out some basic information. And then at the end, we want to go ahead and do our plot learning curve. This is just the x-axis. File name, so we'll go ahead and plot these scores to the figure file. Okay, I think that's everything. Let's go ahead and start running it, but first we have to do a make directory plots, make dir temp, and make dir temp slash TD3. Do a list, okay. All right, so moment of truth, let's see what we get. See how many typos I made. Name NN is not defined. Okay, that's because I must have not done that. So let's go vim TD3 import nn.functional. Yeah, that's what I forgot. Import torch.nn as nn. All right. No module name utils. Okay, so let's do this. Copy. So you would just do a git clone of my GitHub, but I'm just going to grab it from my course directory. Courses, actor, code / courses, Actor-Critic, TD3, tils.py here. All right, now let's try it again. Python main. Name update. It's because I forgot the E at the end of update actor interval, so that's line 136. Update actor interval. Yeah. All right, once again. And it is unhappy about the FC1 or the input of FC1 dims. Okay. Okay, so vim, that's in line 72. No, it's not. That's in my actor network. It's down here though. It's here, and that's because I forgot the tuple unpacking. Star input dims. Okay. Sorry, you can't really see. Let me move my face here. Let's try this again. Agent has no attribute min action. I must have forgotten to save it. So that should be down here. Agent min actions, that's Y. No such file or directory. Oh, I must have a, yeah, self.actor load checkpoint, so I have a load instead of a save. Yeah, that makes sense. Of course I would do that. What else would I possibly do? That is down here. Save models. No. Save checkpoint, save checkpoint. Those are all saves. So if we come up to the actor network, save checkpoint is a save operation. That's a save operation. Interesting. Where does it say that? It says agent.save modules. In save models, self.actor.load checkpoint. Line 274. Oh. Of course. All right. That was a stupid mistake. All right, let's try it again. Okay, so we have a dimensional mismatch. So the first thing to check there is whether or not I made a mistake in the declaration of the, let's see, Critic Networks, C1, Actor Network. No, that doesn't look wrong. That's interesting. So I come down here, make sure the n actions is the same. Input dims, layer 1 size, layer 2 size. Very interesting. So it happens right when I pass a state through my target actor. And it says size mismatch at the second fully connected layer. Oh, I know why. I see it now. Okay, so yeah, right here where I'm saying prob equals self FC2 state. Okay, so that is in my feed forward for my actor network. That should be prob, not state. Right there. All right, let's try it again. This is uncharacteristically many for me. I probably did something similar here. State target actions. All right, so this is embarrassing. This is a pretty rookie mistake. So I was returning prob instead of mu, and it didn't dawn on me until I come down here. You know, I print the number of actions. Let's get rid of that. And it didn't dawn on me until I print out the actual actor network and see that the outputs are correct. So we can get rid of that. And then I come here and see, okay, it's wrong. So what could it be? It ends up having the same output shape as my probabilities. And lo and behold, that is because I'm returning prob instead of mu. That is embarrassing, but whatever. This is real time, real coding. These sort of things happen. So let's go ahead and try it yet again. And of course, I have a typo on line 215. It should be critic underscore lost up backward 215 critic loss. Critic, there we go. Good grief. All right, now it is running. All right, so I'm going to let this finish, and I'll be back in a little while, and we will see how it did. And we are back. So you can see that the agent actually achieved a score of around 270 points or so on average for the previous 100 games, which is considered solved for this environment. However, there is a caveat, and allow me to scroll up. So as I will note, as I edit the video, there was a typo, so that scores should have been score underscore history. So I had to go ahead and run it again. But in the previous run, due to run-to-run variation, the agent did not manage to beat the environment at the end of 1,000 games. In fact, it was still in the negative, but it was on its way up. You could see it was saving a bunch of checkpoints at the end, so it was starting to learn. It just wasn't actually there yet. So given more games, it probably would have gotten there. But 1,000 games is enough to get it in at least some set of circumstances. So I've run this several times, and like 2 out of 3 times or so, we get great results within 1,000 games. So that is twin delayed deep deterministic policy gradients in a nutshell. I left out all the detail because I leave it in the course. Again, I go paragraph by paragraph through the paper and show you the implications for what they say on the final code, how to turn things from paper to code, as well as how to parse their arguments, because it's an incredibly dense paper, incredibly well-written paper, something I would encourage you to read even on your own. Even if you don't buy the course, check it out. The name of the paper is Addressing Function Error Approximation in Actor-Critic Methods. A very nondescript title. I mean, it tells you what it is, but doesn't give you the full scope of the power of the algorithm. So I hope that has been helpful. Make sure to subscribe, like the video, leave a comment down below, and I'll see you in the next video.